Thank you for coming. I'm Falcou. I'm assistant professor from the University of Paris. I will present you some kind of work we did with making cloud programming more available to scientists with the help of C++ libraries. The work I will present there is more than a teamwork. We have two universities working on what I will present and our team of company. I will try to try to go over what Michael will say just before. So thank you, Michael, for actually making my introduction far shorter because you did a great job at presenting all the very intricate problems of direct programming in modern C++.
You're welcome.
We are actually dealing with a bit of higher level problems that we try to make tools for computers, scientists, and more precisely for scientific computing. And so the problem with scientific computing is that you have scientific inside, so which means that applications in science are mostly domain-driven. People writing applications for physics or for biology or for chemistry are very different kind of work. And the users that actually try to make this application working are most of the time not hardcore developers. So they have an hard time trying to keep up with new technology and new architectures. And those users are usually reluctant to changes because they have a strong belief of using a set of tools that are going to work on the problems. And what they miss is all what the computing power of your architectures is actually bringing to them. And if you want to do computing right, what you want to have is to achieve a high level of performance. And as we see during Michael talk, is that the level of performances you know how in a regular machine is 10-fold or 100-fold more powerful than a couple of years. And this requires an expertise that most non-computer scientists may not have or may not acquire easily. And so the problem that we want to state is that people using computer to do science want to do science first and computer stuff afterwards. So our goal is to find a way to build tools for the scientists that want to reap the benefit of all these new architectures, all these new languages from scratch, to get performance, to make their research, their engineering, or the technical achievement possible. So few people are actually experts in both the direct programming side of any kind of problem and the actual field of the problem. So what we want to do there is find a way to make people protected from all the parallel architectures in industry that is coming up, having to deal with new ways to program GPU, new ways to program multi-cores, accessing to the vector extension. Those are something we consider details compared to the actual meaningful values that exist in this application, which stems from the actual domain knowledge. So while doing this, what we also want to do is to isolate the software evolution from the hardware evolution. So your software is written once, and as long as the framework for building the software is automatically updated with your architectures, your software should not change. So what we try to do is try to do this actually using a subset of classical modern C++ programming idioms, including generic programming, template-based programming, and embedded domain-specific languages. So to get some kind of example on this, what we want to do is to introduce Entity, which is our main computing framework written in C++ that actually use this kind of structures to leverage architectures, performances, and we will see how we try to went beyond the classical expression templates way of doing things, and how we're thinking the relationship between hardware and software at the software level allows us to get better performance and better code base. And as an example of applicating this kind of techniques to a new architecture, we get a short overview of our OpenCL prototypes. And I will conclude on some philosophical stuff. So what NT2 stands for the numerical template toolboxes, which is basically MATLAB written in C++ and done right. So basically, you have array-based computing systems that use a MATLAB-like interface and provide high-performance computing by being able to offload parts of all of this computation to the proper architectural subsystem, depending on the computation structures and types. And it's easily extendable in both ways, either for new architectures or for new items. And as a research platform, it allows us to actually try new optimization schemes at the compiler level and try to have a test bench for realistic application of domain-specific language development. So how does it work? Basically, we have a type which encompasses the notion of multidimensional array object that just behave like a MATLAB array. And we have more than 300 functions now that directly work on this on scalar value, and we get basically the same result as in MATLAB. And so basically, if you have a MATLAB code that your fellow scientists wrote because they wanted to get something done, and you want to port it into C++ using NT2, it basically goes this way. So you open your MATLAB file, you copy it into a C++ file. You do a bunch of cosmetic changes because MATLAB syntax is a bit strange, and you add some kind of NT2 headers, and you just recompile it with the library, and your conversion from MATLAB to C++ is done. So let's take a simple example. So we have this very simple image processing algorithm, which is turning RGB three-channel images into a RGB format. So we basically use a simple algorithm where we extract the channel from the original images and compute stuff on it, okay, for actually getting the proper IU and V values. So this is what you will actually write in your MATLAB code, and this is what you will go into write with NT2. So it's basically the same stuff, okay, so every function works on array as compound object, and we have the funky underscore objects that replace the funky column operators in MATLAB that represent the your access to a given dimension. So this is basically extracting all columns and all rows from the first, second, and third channels and put it into these tables, and just before that you can actually compute something with it. So this is just working, but it's actually a bit not performant because we are performing copies by extracting those sub images from these original images. And thanks to expression templates and C++11, we can just keep this expression as a whole and doesn't do any copies, and just replicate it everywhere we need it afterwards. And this actually helps us avoid copies just by saying, okay, it's just meant to be this third channel and just put it there. So it's basically all you have to do. That's a simple translation. We have support for most of the MATLAB operation, including linear algebra. And transformation from MATLAB to C++ is quite fast. And in terms of performances, we are basically beyond 80 or 90% of what you should have if you were writing the same code back here. So this stuff gets used into some kind of real-life application, including automation, navigation for vehicles, pedestrian detection, image stabilization, and so on. And all of this was actually MATLAB code at first and translated using NT2 in a couple of days. So that's the nice part about NT2. But the not nice part was that just before Boost Proto was available, the code base of NT2 was something like 11,000 lines of code. And in this 10,000 lines of code, more than 8 of them were dedicated to make the expression template system works correctly and supporting user interface. And only the actual smart computing stuff was less than 3K lines. And as a way to have an architectural support, we are basically stranded with SAC2 and Ultimate supports. We have a raw prototype for piece threads, and import was stagnant because every time we want to add a new architecture or new functions that was requiring specific architecture supports, we have multiple thousand lines of code to write. So something was not right, and we had to rethink how the software has to be designed. So what we did was jump into the Boost Proto backend at some point. And so before going into this, I may take some time explain what's the domain-specific language is. So domain-specific language is a very well-known concept It's a declarative languages, which is usually easy to use and which is tailored to a given application domain. You cannot do anything. You cannot do everything with it. You can do a subset of what you need to express your problems in a given domain. And the main advantage of domain-specific languages is that the description of your problem in the languages is also the way the computer will solve it. So instead of telling the computer how to solve a problem, you just describe the problem and let the language express how it has to be solved afterwards. And so what's an embedded domain-specific language is basically a DSL, but instead of being a standalone compiler or standalone interpreter, it's embedded in the general purpose languages, and we rely on method programming or just-in-time compilation to turn this small subset of generic languages into something specific to your domain. And EDSL and C++ are basically relying on abusing operator and function overloads to build complex expressions representing abstract syntax tree of your domain-specific language, apply arbitrary transforms on these trees, and generate code afterwards. The very important thing is that when dealing with this kind of code generation process, you can actually carry arbitrary semantic information around the code fragment. So when you are down to the code generation layers, you can actually have all the information you may need to make a meaningful decision with respect to the domain, the application being built, and its architectural targets. And so basically, you write generic code, as in generic programming, and you can make this code aware of all of how it should optimize itself. So basically, if we take a simple example of, for example, a matrix-based EDSL, what you will do is translate this kind of expression, which can be represented as an abstract syntax tree, into a very complex file, which is basically a flattened view of the ISP. And in this tree, we basically have two kinds of information. You have the static information, which is embedded and coded in the tree type over there. And runtime information, which is basically the reference to the actual data that are embedded into the tree. And what you can do is that you can apply a binary transformation on this tree, either at the static or at the dynamic level, and turn this representation into whatever. So in this case, for example, what we do is we just reconstruct the point-wise operation inside a loop nest, and we just decide to slap an OpenMP fragment on top of it. So you run that, the expression template layer goes that inside, you do some little magic voodoo stuff, and you end up with this. And this could be whatever you need. You could have some kind of debug evaluation process that doesn't do any computation, but you just check that everything is correct. You can have support for their OpenMP. We could have vectorized this operation. We could have put this stuff into an MPI block of code. So everything is possible at this point. And the main aspect is that you can do whatever you want on this, with some definition of whatever. So instead of writing this by hand, that's what most people try to do at some point, we decided to rely on Boost Proto. So Boost Proto is a bit of, I think, the most complex Boost library available right now, and the teaching curve is very steep. But put it simply, what Proto is an embedded domain-specific language for defining embedded domain-specific language. I don't think we can get more meta than that. Okay. So basically, it's a generalization, and I almost want to say a standardization of how expression template idioms should be implemented. It basically gives you a standardized object for representing abstract syntax tree, which has both this dynamic and static operation set. And you basically just write, every part of the usual glue of expression templates, like all the operator overloading, the function overloading, the way you have to take care about copies, reference, and whatnot, is basically only done by Proto. And what Proto asks you is to define how your language should be constructed by way of a grammar, and how it has to be transformed into something else by the meaning of transforms. And grammar and transforms are basically two sides of the same coin, and you can switch from one to the others quite easily. And the fact that the grammar and transform are independent from the way abstract syntax were represented means that you can actually write grammar and transforms for a given DSL and reuse it in another because you need the same kind of transformation, except that their language is different. So we can actually have a way to modularize and to capitalize on the definition of multiple domain-specific languages. And which also means that every domain-specific languages written using Proto are by design interoperable. So you can take a bunch of them, mix them one with the others, and you always have a way to know that at this point, I'm leaving language A to go into language B, and I know what to do now. And you could have inter-language support for optimization. So let's say you have a Boost Phoenix Lambda coming into some kind of Boost MSN statement. We could know that we are leaving MSN to go into a Phoenix Lambda and change the way the code is generated. So basically, if you ever wrote a compiler when you were younger, Boost Proto is actually trivial to use. Okay? If you don't, it's a bit more complicated, but it's far more easier than writing all the repetitive expression templates glue by yourself. And basically, if you are going into the compiler mindset, everything becomes clear. You need a way to define your languages by the way of a grammar. What's okay and what's not okay in the languages. All this stuff gets translated by transforms. We exploit the semantic of the languages, and we have transforms that we use the code generation process. Grammar, semantic exploitation, and code generation process. It's basically a compiler inside the compiler. And of course, it's easily extendable using either NPM, Fusions, and other Boost infrastructure libraries. So you can actually do complex either static or dynamic transformation on your tree. So for us, it was actually useful because the NTD code becomes far more scalable because every part of the expression template stuff was basically shipped within Proto, and the code we had to write was basically what we meant to express as what array manipulation library should be. Every optimization we tried to build afterwards was basically making a new Proto transform and putting it into the set of acceptable transform for the grammar. And the debugging were also far easier because you can at any point into your code check that a given Proto expression matches a given grammar. And instead of generating stupid kilometers long error messages, you could have 10 meters long error messages, but which start by something like, oh, dude, your grammar is something messed up, stop there. So the error stuff is actually the first part of the error message you see. You can ignore the bug afterwards, and you know exactly where the problem is. Well, fixing it is another problem, but we know exactly where it is. But it was not enough for us. We needed a way to actually abstract how the hardware has to interact with the actual code and the actual abstract syntax. Most of the time, when you look at state-of-the-art expression templates-based computing libraries, these features are always there. Okay, so you won't bitch about me because I forgot FGL into this list. So if you look at a given set of this stuff, every time they either support a very small subset of what actually is available in modern architectures, or they support it in a very subset of their own functions. For example, IBM has a pretty nice support for SIAD arithmetics, but that's pretty much all, and all the threadings are done at the algorithmic levels. You won't get any OpenMP acceleration when you try to write A equals B plus C times D in IBM. And if you look at UBLAS, which is basically a bindings for a BLAS and LAPACK stuff, the parallelism is coming from the fact that maybe your chosen LAPACK package is already parallelized. I hope I don't say stupid thing about UBLAS because that AG that didn't check. The last time I checked, that one doesn't do that. And the problem is, most of the time when you are writing codes with using expression templates, the architecture support and the parallelism support come afterwards you wrote the expression template system. And this makes it quite hard to actually retrofit the parallel semantic into the language. So what we wanted to have is some kind of Ardois-aware domain-specific language system. And to do so, we are back not to generate programming, but to generate programming. So generative programming is this funky stuff that Czarnecki introduced in 1999 that basically says that instead of writing code directly for whatever application you need, people should write application as a domain-specific description of the application that goes to a translator and pick up information about the structure of the application and select parametric subcomponents from a pool of already written components that may be useful to build this kind of application. And by looking at the actual information about the application, we will pick the best components and build a concrete application. And that's basically what we do every time when we have a policy-based template library or whatever. And so the solution was actually quite evident after we found it, is that if you want to introduce hardware support in this subset of programming systems, we have to apply something there. What we want to do is that we still keep the simple application-driven description, and the translator has to choose between components, and the components may or may not be aware of what kind of architecture they need to support. So what we did was just pile up this onto itself by providing a domain-specific architecture description system. Let's say, okay, my architecture is done this way, and supports this kind of operation and this kind of operation. And this description is used in a generative way to actually generate the components the application constructor will use. So you have to start with your application description, and what we provide is for a given set of architectures, a description of what the architecture is about to do and how it has to do it. And when we compile the program, everything first gets there. So components are being selected for the current architectures and put into the spool. And the application is then built with the architecture-aware components. So it gives you the actual hardware-aware application. And so the challenge then was how to make this happen and how to make it so modern expression template system could benefit from this. So what we did is that instead of directly turning our abstract syntax to implementing our languages into some codes by just working down the tree and generating code on the fly, we decided to segment the evaluation process of the EDSL AST into phases. And each phase is defined by a product transform that basically go from one part of the code generation process to another one. And each time hardware may introduce a specialization point into this process, we have hooks to actually know about it. And to do this, we introduce the notion of generalized tag dispatching to say proper function implementation by looking at kind of argument we were given, the kind of operation we want to represent, and the kind of architecture we wanted them to be run into. And so hardware come back into the EDSL loop by influencing how the code generation process is done. And as we put everything this as a product transform, everything was just adding new transform to our total layers and make it work. So what is this generalized tag dispatching system? So tag dispatching is a very well-known technique of generative programming that use inheritance of a small set of tags that is used for overloading function. Every proper implementation of the standard iterators, for example, use tag dispatching to select different iterators. Is a random access iterator, a forward iterator, and the actual implementation of every iterator's based function in the STL actually uses tags to be dispatched on the correct implementation. And usually, tag dispatching is done using a single element of the function call. And what we did is that we decided to use the yo tagging of every argument of a given function, the tag for the function itself. So we have the notion of function identifiers. So plus as an associated tag, which is plus underscore. And these are actually can be tagged because plus, for example, is an element-wise operation. So the plus tag goes up into the element-wise type tag. And for example, when you have stuff like sum is a reduction. So as a tag say, okay, this is a reduction operation. And we can define the nature of each operation itself. And of course, what it is was computing the tag for the hardware configuration. And lastly, what we do is that when we want to run a function, for example, plus, so as I say, plus is actually defined to have a tag which is an element-wise operation. And the operator plus actually built an object we call a functor that takes this valid tag as a parameter, and we can just call it. And what happened inside? The function call operation of functor basically call another function which is called dispatch that computes the hierarchy, so the tag of the architectures, what we call the site there, the hierarchy of the tag in the function, and the hierarchy of every operation arguments. And this builds the complex types that has, okay, I'm running this kind of operation on top of this kind of arguments, and I'm actually working on this kind of machine. And this task can then be completely externally overloaded. So here is the way we define SCC-based operation between plus operation between two single precision operations. We basically say that, okay, I'm trying to dispatch plus on the SCC3 enabled machine, and I'm taking two SIMD vectors of single precision values represented in an SCC way, which means I'm waiting for N128 operators there, and I'm just calling the inputs. Now, if I wanted to have an AVX support, I just have to change the tags there and make it there and just change the inputs. And this is completely done in an external way. So we can extend the plus operation by keep adding new dispatch overload over the time. And so this is quite the simplest stuff we can do. And for example, this is how we actually handle the arbitrary reduction in an OpenMP-based system. Whatever the reduction, sum, from, min, max. All reduction operation has a tag which says value reduction, and this is actually my actual reduction operation, my binary operation for computing one part of the reduction. This is my unary reduction part when I finish my reduction, and this is my neutral element. Okay. So when I'm doing a reduction over some kind of expression of an OpenMP machine, well, basically what I do is that I put my neutral element into my results. I'm starting a parallel segment in OpenMP, get my local value for the local computation. I'm running a loop over all the elements calling my binary operation for my reduction, and I complete the reduction in the critical section. The important thing is to note that the OpenMP architecture stack is actually recursive. It's parameterized by another site, which describes what kind of core are inside the OpenMP machine. So what we do there is just laying out the OpenMP system for doing our reductions. And when we want to call plus or min or max on the given value inside the thread, we just use S as the site for our pointers. And so, for example, if F is actually something like SSC2 CPU, which means that we are working on CPU with SSC2, everything there will be automatically go through the SSC2 version of all operations. So we just have to deal with the current layer of hardware support. I'm dealing with OpenMP, I'm just writing OpenMP stuff, and I'm delegating the other part of the parameterization to what is beyond me by passing them my inner tag about my architectures. And what we could do is that we could have an MPI tag there with an internal site that would just start whatever MPI needs to make a reductions, and inside every MPI process, we just call the same reduction operation, but this time using the internal site, which may be an OpenMP site, for example. So we get the MPI layers into the OpenMP layers into the SIMD layers. And all what we have to write as developers is the separated support for each of the architectural blocks. And everything gets mixed automatically by the dispatching system. So what we did is that we decided to stop working the IC directly generative code. So we were capturing where hardware can be extending something, and the generalized dispatching was actually providing a solution for that. And so we basically have three phases IC to code conversions. We have a first optimization process that turns the raw IC into a pre-optimized IC. We have scheduled phases where we slice the YO expression into a forest of trees, which is ordered and scheduled by the kind of operation. So for example, if you are doing A equal sum of C plus curve of D, we will extract the two induction nodes because they need a different loop nest than the actual element for the operation, schedule them in some way, maybe just doing one after the others, or if we are on a piecemeal enabled system, put each of them into a futures and wait for the results, and then do the operation on both of the results. And finally, we have the run process, which is basically turns the code generators into actual code. And so what do we do in each phase? So the optimized phases actually do IC pattern matching to an expression construction time to turn large sequence of operation into equivalent but faster kernels. So for example, if you have matrices and we aim to turn A plus B times C, depending on the type of A, B, and C, we will either issue a single FMA node, if we are working with scalars and your architectures has an FMA support. Or if everything is matrices, we will actually generate the optimized DGM code by trying to minimize copies and memory movement between the matrices and the last kernel. And for example, I think everybody knows that computing the inverse of the matrices to solve the system is a bad stuff to do because it's an n cube operation, while solving a linear system is an n square operation. So what we do is that if A and B are matrices and we got this, well, we will silently turn it into a code to a linear solver for you, and we get the square algorithm as a cubic one. So as I say, the scheduled phase segment the IC into a loop compatible loop nest. So we extract different kind of loop nests and schedule them. And we use a node hierarchy using the GTD to split loop or merge loop depending on how they get scheduled. And finally, the run phases is a traditional get an IC generate code phases where we just work down every IC to the scheduled forest and get some actual code generated. But all the code generation going there is actually done with the correct algorithm. So what are we have now? Well, basically now, 82 is still something like 11,000 lines of code, except the actual expression template stuff is maybe less than 500 lines. The generalized dispatching system is maybe 1,000 lines. And all of the 10,000 lines are actually meaningful operation and function supports. And basically, when you want to add a new site, it's basically 100 lines of code. Adding a function for a new architecture, depending on the complexity of the function, is basically between 10 and 100 lines. And we basically are going to support new architectures in something like 2 or 3 weeks. So now the new structures look like something like this. We have the table layer, which is the main user API layers that rely on these abstract system and hardware layers that turn hardware information into meta programs. And we have this abstract programming layer that relies on Proto and fusions to deal with all we need at the code generation level. And what we can do now is that we can have arbitrarily rich semantic to table and turn it into something more meaningful, like a polynomial, an images, a matrix, or whatever, or rigid transform. And by doing this, we basically have information about the domain that we can actually catch into the hierarchy system. And yet, we are going to go through all the system of code generation and get the best parent performances out of it. So, for example, support for OpenMP was basically adding the support into the system. We have 4 overloads for the run phases, 1 for each big types of loop nest, and we have 1 new allocator, so we try to minimize false sharing. And for example, with the next-gen stuff, we basically now have a complete support for all the SSC variants from 1 to 4 point something. We have support for ActiveX and for some ActiveX variants for example, game consoles. It took us 2 weeks to actually support ABX. Most of these 2 weeks were actually hitting the keyboard to write the incorrect intrinsic codes wherever they were needed. We have a prototype for AMX2 that works into the Intel simulator for now, and the same for the actual Larby and Larry system. Just wait for an actual machine to be benchmarked. So we say architecture says GPU because you are all the new fad right now. So what we decided to do is try to have a prototype of OpenCL support. So OpenCL is designed as a standard for multi-cores and many-core systems that use runtime kernel and just-in-time compilation to actually address the architecture's systems. So basically, you have your OpenCL kernel, which is looking like a big, huge string somewhere that get passed to an OpenCL compiler at runtime, and that give you a kernel back up into the C++ that you can call like a function by passing a proper data here. And depending on you are working on the GPU or the mythical system, this gets presented into something different. So the idea was, can we actually keep the 82 interfaces, and whenever we are on OpenCL enabled system, we can just turn the code generation into an OpenCL code generation system? Well, that was quite easy. Basically, we just modified the schedule path. What we do for OpenCL is that we split the IC as usual, and we replace each IC by a function that is about to generate the equivalent of OpenCL kernel string. Okay, so we walk down the tree, and for every operation in the tree, we generate the proper OpenCL string. And what we do is that once we have that, we are computing a static hash code for the your IC structure. So we remember that we only compile something structured this way, and we don't compile all operations every time we enter it. Which means that if you have one line that says that A is equal to B plus C times D, and 10 lines below you have Z equal W plus Y times Y, we will use the same kernel and just sending different data. And so you will pay the OpenCL compilation only once. And the run path basically gets this kernel into the main core systems, takes the data and starts some data streaming from the CPU memory to the GPU memory, and retrieve everything we need to make the core working. And we fire kernel calls on each of the forest of ISP in an asynchronous way, so everything is basically scheduled by the cards. So for example, this is a random code we could write, and if you don't do anything and you have an OpenCL enabled systems, we will basically look at what the size of these things are, and if they are big enough compared to your system's specification, this may be turned into an OpenCL kernel. But if you are sure that you want to go onto the GPU, you can actually force the evaluation to be done on GPU by just adding a new setting. So this works. I mean, it works with direct expression call. It also works with functions, because if your function actually takes arbitrary AST, the AST evaluation process is delayed inside the function. So this function may also generate OpenCL calls if you pass OpenCL enabled expression to it. But as it's a template, you can actually pass regular values to it, and you get the regular values computation on the CPU. And you don't have to rewrite your higher level function, because the evaluation process will go through the function boundaries. So what does it do in terms of performances? Because I was speaking of high performance computing all this long for 30 slides and didn't show performance yet. So we just keep these stupid examples that were generating constant signals. It runs in 520 milliseconds on a single core GPU, which are exciting. It runs in something like 140 something with your 4 cores enable. It goes down to 36 when you activate a CC3. And then we run it on the GPU. So the first run is abysmal, because we are paying all the costs of transferring the data, combining the kernel, generating the string and whatnot. But once you did this first run, you basically go down to something like 20 or 50 milliseconds for the same code. And writing the manual OpenCL again to get the stuff working basically just by 0.2 milliseconds, which means that the code generation is as close as the optimality of the code. And when we compare to other solutions like EDSL, which is basically OpenCL oriented expression template library for computing, or Accelerate, which is commercial products that turn MATLAB codes into OpenCL codes, we are basically within 10% of their performances, and we exhibit the same crappy first runs and great performance behavior. So we are pretty good on this. But it's still a prototype, and I think there is a lot of stuff which is not wrong to what we work on. We are working on that. So as a conclusion, parallel computing is not only for computer scientists, it's mainly for scientists. And we have to do a great deal of efforts to bring to the scientists tools they can actually manage to use while getting the highest level of performance they may want. And you see embedded domain-specific languages, especially in C++, as an efficient way to build such tools. But we have to keep up with what the hardware is actually giving us, and we have to be conscious about what the new hardware systems would be have to modify the way we compute. So our place and our research shows that you can build software library using generative programming and generative programming that can actually solve a large chunk of data queries related problems while being easy to use and giving you a nice share of performances. And like actual normal languages, we have to think about the fact that embedded domain-specific language need a way to know about the hardware they are run on. And that's what we try to do with what we were doing. And integrating the hardware description into the system code generation actually increases the portability of the tools and replicability of the applications. So what are we doing now? So we plan to have a public release of 82 rather soonish. So I don't know if people were there in Boost Proto 2010. Maybe Baron was there, I don't remember. I have this in my side for about 2 years now. But I mean it this time. We are really close to having something to be released. Meanwhile, if you doesn't feel to lose sanity or put your aim into some kind of work in progress code, we have an open GitHub repository where we can look at what we are currently doing and trying to get to the release. We also have publicly MATLAB to NT2 compilers that were just able to look at MATLAB code directly and pass it and just generate the equivalent NT2 code and compile it directly from MATLAB. This is actually working quite nice. We also have a prototype for single source CUDA support in NT2, which basically means you write your CPP code and we will write the .c kernel for you. Okay. This is still a bit preliminary, but it's starting to work. And we have a PhD student working on the distributed level, either with API or HPX, which is the parallel runtime designed by the Stellar Group in University of Louisiana, mainly Alton Kaiser and all these guys, which I actually advise you to go and see the talk of Thomas Serrer about that later in the process. So when those are basically done, we try to have all-encompassing system for distributing to small grain science reports. And we are currently looking forward into the futures, and when we say futures, we mean STD futures. Okay. After playing with a lot of stuff in this thingy, we actually found out that the future abstraction and the asynchronous call systems is actually a nice higher level backend system for more distributed or shared memory systems. And what we are trying to do now is to have a single future-based backend for everything above SIMD and make GPUs, threads, and distributed systems fit into that. So we don't have to think too hard to add a new higher level of hardware support. We just have to provide the future support for it. We also have experimental research going on for NT2 and embedded systems. So either regular embedded system, like for example Android, ARM chips, Android OS, and stuff like that, or more exotic one, where we have like something like 4K of memory and thousands of cores on something that you can only program with the stupid assembly languages. We try to see if we can push the just-in-time approach we use in OpenCL to target these architectures where running a C++ compiler is out of question. And so what we try to do, but this is a far more long-term goal, is try to have generic approach to parallelisms. The same way we have a generic approach to solve a lot of sequential problems, and we actually did with a lot of success with STL and Boost and whatnot. And what we think is that we should have some kind of generic approach dedicated to solve the parallelism problem at the library and user level. And I think we are currently getting some kind of insight on that into our research. So thanks for your attention.
Thanks for reading my tomorrow talk about
the
OpenCL section. Second, I have a question. What about, or you talked about selecting computational path based on text and based on your site.
Yeah.
Is this completely static? Tag dispatching is static, I think, right?
Yes, it is.
And then you have to compile your program for your specific architecture that you are going to use with.
Yes.
Is that right?
Yes. So the architecture description and detection is currently static. But what we do is that usually, I didn't put it there because the slide was too small, but usually when we enter a potential architecture support layers, what we do is that, okay, I have these architectures at my disposition. I can do something at this level, but is it meaningful? And the answer to the is it meaningful to use this architectural level question is usually something you have to decide at runtime. Because you may, for example, need how many data should I process, or what is the type of the data, do we have any pending stuff to do before starting it. So what we usually do is that if we can infer the answer to this is it meaningful question, we statically branch to the optimal code. And if we can't, what we generate is a couple of branches, one using the architectures and one not, and we use a dynamic branching in runtime to say between both. So basically, you can run the code with different number of data to process or different number of calls and whatnot, and we will try to accommodate this change at runtime. And it's the same for the GPU. We look at how many data we have to process and what are the specification of the GPU. And if we have too few data to process, we just don't call the kernel and go through the regular CPU code. So we basically try to do most at compile time, because this will ensure that the optimal path is selected. But sometimes we cannot, and we just output some kind of runtime selection between different variations of the kernel code.
So it probably will be difficult to incorporate NT2 into some, like a black box of MATLAB or you probably would have to compile every possible path.
Yeah, I see. Well, in this case, what we advise is that you actually write your code once, because the code is basically every time the same. And yeah, you compile it for different kind of architectures, and you let the system select the proper one. This is something we want to improve because it's a bit cumbersome at the moment. But our main targets, scientists target, are usually people that have very specific machines and they run stuff on it. And the machine change once in a while, but once they compile for a given set of architectures, they are pretty much happy with it. But we are conscious about other use cases, like for example, regular application on the desktop machine that doesn't know if you have this or that support after you build the binaries. So we are trying to get some kind of better system for this kind of use cases. But currently, yes, you have to rebuild the stuff if you change the architecture.
Okay, what follows is an opinionated, polarizing, but in my opinion, not silly question. Does table support zero-based indexing?
Oh! If you choose, so they can. So I don't know if I have an example. Oh yeah, I changed the example. I should have not. What you don't see there is that you have a second template parameters of there, which is what we call our settings pack. And a settings pack can take an arbitrary list of content type options. And one of these options are actually, is my index starting from 0, 1, or something else? Okay, if you want to have table with indexing starting at -50, you can do this. You can also change the storage order or the way you actually lay out the memory, but it's all optional, and by default, we decided to be a complete clone of MATLAB. So this means that table is column measures with one-based indexing.
You mentioned the settings there. Might be about, what kinds of layouts you may have?
Well, so you can change the storage order, you can change the indexing, you can change the way you store structures. So if you have, for example, complex, you want a table of STD complex. If you don't say anything, what you will have in memory is a bunch of STD complex one after the other. So real imaginary, etc. Which may be detrimental in some algorithms. And if you want, you can pass a setting which is called de-interleave. and that will automatically turn the array of structure into a structure of array. So it will basically be storing two arrays, one for all the real parts and one for all the imaginary parts. And so some algorithms go faster this way. We have this. We have a way to change the storage model. So is it a dynamic allocation or a stack-based allocation? We can change the way, we can also specify a complete custom memory block structure. So if you want to have use STD vector instead of our old buffers for holding memory, you can just say that the buffer is STD vectors, and we will use that. Well, if you work with STD vector, we have a set of concepts that your buffer stuff should support. You can also have we have a setting which is called sharing. That means that the table is not the owners of the memory allocate, so you can pass a pointer for some third-party drivers or application, and you turn it into an MT2 table without doing any copy. And recently we added a release method on tables, so we can get the data back out of the table that the MT2 allocated and pass it to some third party without any copy, leaving the table into an empty state, which is basically half of the move segmented stuff. So we are very conscious that we cannot be compatible with everything out of the box. So instead of trying to find the feature creep stuff, we decided to have a very small range of functions like this that help you interacting with whatever, and we let people write bindings to whatever stuff they need. So we have an OpenCL backend in the work where you can actually grab an OpenCL matrices, turn it into an MT2 table, do stuff on it, and go back into OpenCL. And we are working on adding more and more of these bindings as time goes.
Okay. What was your experience of working with Boost Proto? Do you need a PhD for that?
Well. So I will give you two answers. One which is obviously yes, which is where I don't think because I actually had a PhD in computer science and I was working on compilers before, so I actually grabbed the stuff quite quickly. Now the non-biased answers. Boost Proto learning curve is really steep, and it's really well. It's not because Boost Proto syntax or concept are complex. I mean, it has a few quirks, and you can get around it quite fast. But the main problem is that there is a cognitive dissonance between what people think expression templates are and what they actually are. And they try to do stuff with Proto they should not. And so they get frustrated and bitch about the library and, oh well, whatever. So, if you are going into the mindset of what I am currently building is a compiler, so I need to define what my language are and how I should work on it and what the code I want to generate from that. And forget about your writing C++ code with funky metaprogramming stuff and function and whatnot. It gets easier. You have to look at writing protocol as if you were writing a compiler in some kind of strange language, but which is not C++. It happens to look like it, but it's not. And after that, it gets a bit better. Now, I'm currently commenting Proto with Eric and Christoph Henry for a couple of years now. And we are trying to get people interested in Proto. And what we need is people actually bitching about how they were trying to use Proto in its face, so we can actually improve it and improve the documentation, the examples, and maybe have some kind of fine-grained progressive tutorial. So, yes, Proto is hard, but not for the reason people think it is. It's not because of the C++ voodoo magic which is inside, but because of what we are trying to achieve with it. And writing a compiler is not a simple task, and Proto is not a simple library for these very reasons. Now, we are very open to make it easier. We try to get some kind of, what's the name of that? Proto quick start stuff session in Discord. I'm trying to get Proto tutorials wherever I can. What we really want to do is that we really want to push Proto as a very meaningful tool for doing this, so people stop writing crappy expression template code all by themselves and bitch about. And what we really want to do is actually try to see if the experience we get from Proto building could be translated into something we can propose to the standards. Because we think that being able to manipulate C++ IST directly from C++ is actually meaningful features. But what people are actually doing, using expression template for years, so this means that the idea is actually useful and doing useful stuff. So we try to make it easier to use. So yeah, it's hard, but you should not require a PhD. I have a couple of undergrads that actually do quite well with it, so that lowers the bar a bit. But yeah, the main problem is the learning curve, and we try hard to actually get it better. And I'm very open if you have any suggestion how to do it. And I think I'm completely over time. Yeah, okay, thanks.